The vast expanse of the cosmos may seem infinite now, but all of this emerged from what we call the singularity. At least this is our present understanding of the Big Bang Theory. But the James Webb Space Telescope has unraveled deep secrets of the birth and evolution of the universe itself, and what it has shown us is baffling. Renowned physicist Brian Cox announced that James Webb's remarkable discovery could destroy our understanding of the universe as a whole. Join us as we explore these recent celestial discoveries that will change everything. The James Webb Space Telescope, or JWST, is nothing short of a marvel in modern astronomical exploration. Named after a prominent NASA administrator, James E. Webb, this telescope is a major technological advancement over its predecessor, the Hubble Space Telescope. The JWST resulted from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency. JWST exceeds its predecessor's capabilities with its cutting-edge technology and a design optimized for studying the cosmos with unprecedented detail. Forget foggy shadows, the JSWT delivers crisp and sharp images of distant celestial bodies that had never been seen before. The telescope operates primarily in the infrared spectrum, which means that it can peer through cosmic dust and capture celestial objects that were hidden from sight all this time. Owing to its 6.5-meter primary mirror, composed of 18 hexagonal segments, the JSWT all but dwarfs the Hubble's mirror in size. It is positioned nearly 1.5 million kilometers away from Earth at the second Lagrange point, or L2, and orbits the Sun in sync with Earth. This allows it to maintain a stable and uninterrupted view of the universe. But the thing with peeking into the distant corners of the universe is not all about the light years in between, it also involves time travel, well, kind of. You see, the JSWT employs infrared instruments to observe distant celestial objects and events dating back billions of years. The light emitted by these objects, of course, is that old, and it also stretches as the universe continues to expand. This is known as the redshift. Simply put, what could have once been observed in the visible spectrum now falls under the infrared wavelength or longer. Thankfully, the JSWT can detect infrared light emitted by celestial bodies at extreme distances. JWST can thus help us study the birth of stars, explore the formation of galaxies, and investigate the atmospheres of exoplanets. This allows scientists to unravel the mysteries of the early universe and dive into the depths of whatever happened shortly after the Big Bang. Most recently, it has made a groundbreaking discovery. We detected an inconceivable mass of galaxies at the edge of the observable universe. And it's a big deal because it challenges the validity of the Big Bang Theory and forces a re-evaluation of our fundamental cosmological assumptions. More on this later, but for now, let's dive a bit deeper into how we got here in the first place. The history of space exploration dates back to the times of early civilizations like the Greeks and Chinese who observed celestial bodies, laying the groundwork for our understanding of planetary motion. Newton's laws in the 17th century provided a theoretical framework for space travel. Edwin Hubble, an influential astronomer, made groundbreaking discoveries in cosmology and observational astronomy during the early 20th century. His observations in the 1920s revealed that many distant nebulae observed in the sky were actually separate galaxies located far beyond the Milky Way. This discovery revolutionized our understanding of the universe's size and scope. Hubble also established a relationship between a galaxy's distance and its recession velocity. This relationship, now known as Hubble's law, indicated that galaxies farther away from us were moving away at higher speeds, thus providing us with compelling evidence for the expansion of the universe. Hubble's work transformed our understanding of the cosmos forever. The next big thing in space sciences was post-World War II, when the space race ignited with the Soviet Union's Sputnik in 1957 marking the first artificial satellite in orbit. Yuri Gagarin's 1961 orbital flight and the Apollo 11 moon landing in 1969 were pivotal achievements of the USSR and the USA in this space race. Fast forward to 1990 and advancements from past space missions allowed us to launch the Hubble Space Telescope to peer at the universe with unprecedented clarity. The Hubble Space Telescope, or HST, achieved remarkable milestones and delivered breathtaking insights into the universe. It unveiled the vastness of space and reshaped fundamental concepts in astrophysics. For instance, the HST captured the iconic Pillars of Creation image in the Eagle Nebula, which showed a star nursery made up of colossal columns of gas and dust. The Hubble Deep Field is another mention-worthy snapshot of a seemingly empty patch of space actually inhabited by thousands of galaxies. The HST also studied exoplanet atmospheres, detecting elements like water and organic molecules in distant worlds, which signal the possibility of habitability beyond our solar system. It also tracked the evolution of the closest observed supernova, SN 1987A, shedding light on the life cycle of massive stars. These accomplishments solidified the Hubble Space Telescope's legacy as a cornerstone of modern astronomy, inspiring scientific inquiry and captivating the world with its astonishing cosmic revelations. Its successor, the JWST, was launched to add to the technological progress and lessons learned from the Hubble. One such example is our understanding of the beginning. The beginning of everything. Today, the Big Bang Theory stands as the prevailing explanation for the origin and evolution of the universe. Of course, it was not always like this, and who knows where we'll go from here. We know for a fact that some 13.8 billion years ago, the universe came alive as an infinitely hot and dense singularity. This singular point rapidly expanded, initiating the universe's expansion and the subsequent formation of matter, energy, and the fundamental forces governing the cosmos. As the universe expanded, it cooled. This was when particles began forming, leading to the creation of atoms, stars, galaxies, and the diverse structures we observe around us today. The theory also explains the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the universe. Though it is accepted without question today, the Big Bang Theory encountered serious skepticism and challenges in its early stages. It had to compete with alternative models like the steady-state theory, which proposed a universe without a singular beginning. People also questioned the lack of evidence supporting the initial singularity and the mechanisms behind the sudden expansion. The theory also failed to account for certain observations, such as the uniformity of the cosmic microwave background radiation across the sky and the formation of galaxies and large-scale structures. But with time, most of these objections were put to rest. One pivotal piece of evidence came with the detection of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson. This remnant radiation, predicted by the Big Bang Theory, is compelling evidence for the universe's early hot and dense state. Subsequently, observations from space missions like the COBE and WMAP satellites, along with advancements in telescopic technology, further corroborated the Big Bang Theory. Plus, precise measurements of the cosmic microwave background radiation have aligned remarkably well with the predictions made by the theory. However, all of this may be overshadowed by the revelations made by the JWST. The James Webb Space Telescope is equipped with advanced infrared instruments and can thus peer through cosmic dust clouds. This allows it to detect the faintest, oldest light in the universe and observe objects that formed shortly after the Big Bang. The telescope operates primarily in the infrared spectrum, and since infrared light has longer wavelengths than visible light, it allows JWST to capture different aspects of celestial objects and phenomena. Infrared light can penetrate interstellar dust clouds that block visible light, which was a major limitation for the Hubble Space Telescope. The JWST can thus observe star-forming regions, stellar nurseries, and the birth of stars obscured by optical telescopes. Moreover, the cooler objects in space emit primarily infrared radiations, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As these celestial bodies move away from each other, the light waves they emit get stretched out or elongated. This stretching of light waves causes a shift toward longer wavelengths, shifting visible light toward longer wavelengths, such as infrared. The farther away an object is, the more its light is redshifted due to the greater expansion of space between the object and the observer. JWST's infrared capabilities allow it to detect these redshifted signals, capturing light from the early universe and providing insights into its formation and evolution. Some energetic events, such as black hole formations or the birth of new stars, emit predominantly in the infrared spectrum. The telescope can study these otherwise obscured or invisible phenomena. JWST thus complements the observations made by optical telescopes like Hubble. Its enhanced sensitivity and ability to detect infrared radiation allow it to see farther into space and deeper into cosmic history, unveiling hidden cosmic wonders and providing a more comprehensive view of the universe's evolution. The JWST is thus our window into the earliest stages of cosmic evolution. Most recently, it has unveiled something so shocking that we may have to reconsider the whole cosmological model of the universe. We have discovered astonishing masses of galaxies at the very edge of the observable universe. These ancient galaxies existed mere hundreds of millions of years after the Big Bang and nestled at the cosmic dawn. The thing is, we're not sure how such massive structures formed so early in the universe's history. We may as well have to re-evaluate our understanding of the formation and evolution of galaxies in the early universe. Observing early galaxies is our only way of unraveling the mysteries of cosmic origins. By studying these early galaxies, scientists can understand how galaxies, stars, and planetary systems emerged and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had inherent limitations in observing the early universe. The primary constraint lay in its inability to effectively penetrate cosmic dust and detect infrared light emitted by ancient galaxies. Older telescopes predominantly relied on visible and ultraviolet light observations, making it challenging to peer deep into the early universe where these wavelengths are absorbed or distorted by cosmic dust and gas. Earlier telescopes offered only limited insights into the universe's infancy, leaving vast stretches of cosmic history obscured from observation. The James Webb Space Telescope marks a transformative breakthrough in observing galaxies from the universe's infancy. Unlike its predecessors, the JWST can and does observe celestial objects that formed within a few 100 million years after the Big Bang. By leveraging its infrared sensitivity and advanced imaging capabilities, JWST has unveiled a treasure trove of ancient galaxies, offering unprecedented clarity and detail in understanding the universe's formative epochs. So far, the preliminary outcomes from the James Webb Telescope's observations have stirred ripples in our established cosmological models. The detailed data from JWST's deep observations of early galaxies challenge some aspects of prevailing theories. These initial findings have prompted cosmologists to re-evaluate fundamental principles governing our understanding of cosmic evolution and structure. The discrepancies between the observed data and theoretical predictions have led to intense debates within the scientific community. These observations uncovered a higher number of galaxies in the early universe than predicted by existing models. Based on this data, there was probably a much more complex and rapid formation process involved than previously theorized. Also, some of the observed early galaxies appear more evolved than anticipated. This raises questions about the timeline and mechanisms driving galactic evolution. Their perceived maturity challenges conventional models that predicted slower development in the early universe. The detection of an inconceivable mass of galaxies at the edge of the observable universe also challenges the presumed distribution and arrangement of cosmic structures. We obviously have a much more intricate and denser cosmic web than previously thought. These observations raise intriguing questions and avenues for further exploration. The presence of massive structures in the early universe challenges some early models of cosmic structure formation, which predicted a more uniform distribution of matter at those epochs. The discovery prompts scientists to refine models to better explain the formation of such massive structures in the early universe. Moreover, understanding how such massive structures assembled relatively quickly after the Big Bang presents a puzzle. Explaining the mechanisms behind their rapid formation without violating fundamental principles of cosmology is a challenge. We have unveiled surprising discrepancies in the conditions of the early universe compared to predictions based on existing models. These disparities could imply previously unrecognized physical processes, unexpected conditions, or unidentified cosmic phenomena. Long story short, these deviations have forced scientists to re-evaluate and refine our cosmological models. For now, all we can say is that we need further research to incorporate these unexpected observations into a more comprehensive understanding of the universe. Initial observations often unveil tantalizing glimpses of the cosmos, but subsequent in-depth analyses occasionally reveal discrepancies. For instance, early observations might suggest specific properties or formations within distant galaxies that, upon further scrutiny, show variances in their composition, structure, or evolutionary pathways. Long story short, cosmic phenomena are very complex and demand meticulous analysis for us to be able to understand their true nature accurately. Spectroscopy, for example, can help us unravel the properties and history of celestial objects. It involves dissecting the light emitted or absorbed by cosmic entities. Based on the properties of the light emitted and absorbed by celestial objects, spectroscopy reveals detailed information about their chemical composition, temperature, density, and motion. Spectroscopic analysis helps us understand the origins, evolution, and contribution of celestial bodies to the cosmic tapestry. JWST has unveiled numerous cases where initial observations differed from later analyses. For instance, initial observations of distant galaxies indicated a presumed elemental composition, primarily dominated by lighter elements like hydrogen and helium, consistent with theoretical predictions. However, spectroscopic analysis conducted using JWST showed us intriguing variations in elemental signatures. We detected heavier elements or compounds that were previously either undetected or underestimated in the early universe. This challenged conventional notions about the early universe's chemical makeup and the mechanisms responsible for their formation and dispersion across cosmic distances. Similarly, initial assumptions regarding the galaxies in the early universe were inferred from preliminary observations. These assumptions suggested a relatively uniform pattern of development and organization. However, more comprehensive investigations conducted by JWST revealed a much more diverse and complex array of structural configurations within these galaxies. These discrepancies have reshaped our understanding of evolutionary trajectories, implying that the mechanisms governing the formation and evolution of galaxies in the early universe might be far more intricate than we thought was previously possible. On the other hand, the JWST has also confirmed several earlier hypotheses and observations. For instance, the spectroscopic measurements conducted by JWST validated the presence of hydrogen, helium, carbon, oxygen, and nitrogen within cosmic objects. The signals observed from cosmic objects highlighted emission and absorption lines that corresponded to these elements, confirming their existence in distant galaxies and celestial bodies. Thus, the findings corroborated theoretical predictions in this regard. The lambda cold dark matter model is the most widely accepted one. According to this model, the universe began with the Big Bang and consists of ordinary matter, dark matter, and dark energy. Dark matter, though invisible, influences gravitational interactions. Dark energy fuels the universe's accelerated expansion. Over billions of years, galaxies formed and clustered, shaping the large-scale structure we observe today. However, since several predictions made by this model have been challenged by the recent findings of the JWST, we can't help but wonder if we have other options. And we do. One such example is the cold dark matter model, which proposes that the majority of the universe's matter is in the form of dark matter. This unseen matter differs from the familiar atoms and particles constituting ordinary matter. It does not interact with electromagnetic forces, including light, making it invisible to most detection methods. However, it exerts gravitational influence and moves sluggishly in the early universe. This slow movement allowed them to clump together gravitationally, forming the initial seeds for the large-scale cosmic structures observed today, such as galaxies, clusters, and cosmic filaments. Our understanding of the cosmic microwave background radiation supports the predictions of the model at the large or galactic scale. However, challenges arise at smaller scales, where we have discrepancies in the model's predictions regarding the internal structure of galaxies and the abundance of small satellite galaxies around larger ones. The quasi-steady-state cosmology is another proposal that suggests that the universe has no distinct beginning or end. Instead, it follows a cyclical pattern of continuous expansion and contraction. This model also challenges the Big Bang's singularity by proposing that matter creation occurs continuously throughout cosmic history. The model remains largely speculative due to its deviation from conventional cosmological models and the lack of direct observational evidence supporting its cyclical nature. But stumbling upon hard evidence may only be a matter of time. Another explanation for the universe is the mirror universe hypothesis, which speculates about the existence of a parallel or mirror image universe running alongside our observable cosmos. The mirror universe can have its own distinct physical laws and possibly even mirrored particles, potentially explaining various cosmic mysteries and phenomena. The basis of this model emerges from theoretical considerations due to the absence of empirical evidence or experimental data. However, it remains highly popular among people who subscribe to this view of the cosmos. The digital simulation hypothesis is yet another cosmological explanation that suggests that our universe could be a sophisticated computer simulation. Proponents argue that our reality might be an intricately programmed simulation, much like a highly advanced virtual reality construct based on the fundamental constants of nature and the observed regularities in the universe. This model stems from philosophical considerations and thus faces great challenges in providing empirical proof or disproof. Lastly, we also have the multiverse theory, which is another popular proposition in cosmology. This model proposes the existence of multiple universes, each with its own distinct set of physical laws and properties. And our universe is just one among an infinite set of universes, each with different constants and possibly dimensions. Of course, we can't directly observe or access other universes, and it is for that reason that it remains largely speculative, since we can't verify alternate realities as of yet. Although alternative cosmological hypotheses are not as widely accepted as the lambda cold dark matter model, wasn't this also true for the latter early on? While confirming or refuting these speculative theories remains a daunting task, we may have to turn to these if our present cosmological model fails to stand the test of time. While the recent revelations are eye-opening and change a great deal about how we look at the cosmos, many experts believe that the JWST hasn't refuted the Big Bang theory. Instead, these observations have enhanced our understanding of cosmic history. Experts widely support the Big Bang, and JWST's discoveries align with the predictions of the Big Bang. The presence of massive galaxy clusters at the farthest reaches of the observable universe suggests that gravitational forces were at work even in the early universe. These clusters likely formed gradually over billions of years through the gravitational attraction of matter, consistent with the Big Bang's predictions. Moreover, the fact that we can see these massive structures at the edge of the observable universe implies that their light has taken billions of years to reach us. It offers a glimpse into the universe's past, showcasing the state of cosmic structures at earlier stages, and supports the theory's predictions about the universe's evolution. However, these observations also introduce discrepancies that demand unbiased scientific attention. The James Webb Space Telescope has opened new vistas, allowing us to peer back in time and explore the ancient realms of the universe. With the JWST, we confront a cosmological landscape teeming with new questions and intriguing possibilities. The uncertainties unveiled by JWST challenge established cosmological paradigms, prompting a re-evaluation of our understanding of the universe's birth, evolution, and fundamental principles. The most important thing for us to do in light of such revelations is to remain open to reimagining our cosmic narratives. These recent discoveries are but a prologue to the ongoing saga of cosmic exploration. We need further research and continuous innovation to push the boundaries of scientific inquiry in the cosmological arena. The quest for cosmic truths persists, urging us onward in our exploration of the vast unknown. Thanks for watching. Don't miss this video you see on your screen right now, it's truly unbelievable.